Last speaker is Helle Hansen from Eindhoven.
Thank you. I also want to thank the organizers for inviting me here. I'm pleased to be here. And will also be like what Maya was saying, I'm not sure how well my talk will fit into the general theme of linguistics and quantum computing, but at least it involves algebras, although I believe not in the sense that we heard about yesterday. So the coalgebras that I will talk about are the kind of coalgebras that Bart was talking about and what Dirk and after me Raoul will talk about. So it's the view that coalgebras are a general form of state-based system where the type of the system is captured by the functor F. So in this view we get general notions of system equivalence and system behavior as by similarity, and well, the system behavior is given by finding coalgebras. So finding coalgebras is like a domain of abstract behaviors. Now what I'm going to talk about is operations on finding coalgebras, so operations on F behaviors, if you like, and in particular ones that are defined by an operational kind of rules that come from structural operational semantics. And well, moreover, I'm interested in looking at operations that come from such rules, and can we extend the rules to define the corresponding pointwise operations on the coalgebra, which is f to the power a. So if you have operations on f behaviors, I want to look at pointwise extensions to operations on f to the a behaviors. So before I go on, I want to say that this is joint work with Bart from the University of Cambridge and Warsaw University. And if you become interested, there is also a paper which will soon appear. So, just to repeat the definition of coalgebra, it's I only consider coalgebras for set functors. So an F-coalgebra is simply a function from x to f of x. And well, as I already said, a final F-coalgebra is like a domain of F behaviors. So we're going to look at a few examples that are relevant for this talk. One of the simplest kind of coalgebras that you can look at are coalgebras for b times x. So we call them stream automata. So in this notation, we say that x goes to x prime with output b if the coalgebra maps x to the pair b x prime. So the final coalgebra is the set of streams over b. Simply, if you look at a state x, you can look at the stream of b's that it can generate. And the coalgebra structure is given by the head and tail operations on streams. So I think this is probably the example that everyone will know if they have some coalgebra example. So another example is Mealy machines. So these are input-output automata. So a Mealy machine with input in A and output in B is a coalgebra of this type. So we write x goes to x prime on input A with output B if this is the case. And the F behaviors are causal stream functions. So they are functions from A streams to B streams for which the nth element of the output depends only on the first n elements of the input. And the coalgebra structure is obtained by what we call initial output and stream derivative. But it's, if you understand the way the coalgebra works and the associated input-output function that you get from the state, it should be clear what the definition of this final coalgebra structure is. So we will define operations on F behaviors by distributive laws, and they're usually phrased as distributing syntax over behavior. So if sigma is a signature functor, so it's the set functors are associated with an algebraic signature, and F is the functor for a coalgebras, then such a natural transformation gives us F-coalgebra structure on the set of F behavior. Gives a sigma algebra on the set of F behavior simply by composing the sigma of the final coalgebra map with the natural transformation. You get the F-coalgebra structure on the sigma of C, of Z, and by finality you get this unique map into the final coalgebra, which is the sigma algebra on Z. Similarly, for a natural transformation of this type, you can do the same trick. So this second type will, is a little more general. So it allows you certain it gives a more general specification for it. So this method of specifying operations on finite coalgebras comes from structural operational semantics, as proposed by True and Plotkin in their seminal paper of 1994. But it's also been further elaborated by Falk Bartels and Bartek Klin in particular. And so just to briefly say what structural operational semantics is about, usually you think of it in terms of a process theory. So a process is specified by some term over your signature. And given a set of rules, you can generate the operational semantics in the form of a labeled transition structure, or as we would see more generally, in the form of a coalgebra of some functor f. So these rule formats, they will correspond to distributive laws of different types. So we already saw the first two here, but more generally you can replace the sigma on the right-hand side with the free monad generated by sigma. So it allows you to use in your rules not only terms of depth 1, but arbitrary terms of the sigma. We will see some examples in a moment. So a model for such a lambda is called a lambda bialgebra. So if lambda distributes sigma over f, then a lambda bialgebra is a carrier set x, which is both a sigma algebra and an F-coalgebra. And moreover, the algebra and coalgebra structure must interact properly according to the distributive law. So these lambda bialgebras, they form a category themselves. The morphisms are just the maps between carriers, which are both algebra morphisms and coalgebra morphisms. And as we already saw before, if you have such a distributive law, you get operations on the finite coalgebra, and it turns out, in fact, that the lambda bialgebra that you get is a finite lambda bialgebra. And dually, if you have an initial, an initial sigma algebra in form of terms, and this gives you, in fact, an initial bialgebra. So this generation of operational semantics gives you the coalgebra structure on the terms, and well, this turns out to be an initial bialgebra. So what's very nice about this this view on operational semantics as lambda bialgebras is that it turns out that f bisimilarity, so the map you get from an arbitrary F-coalgebra into the finite coalgebra, is also congruence with respect to the algebra part. So in other words, it allows you to do compositional reasoning. So if you compose two bisimilar objects, then you are going to get something which is bisimilar. So to look at some particular examples, we consider stream operations. So the functor f is says set x to b times x, and for a binary operation, the sigma is just x times x. So assume we have some plus operation given on the set of outputs, we can define some O plus operation by the following rule. So the O plus is an operation on the streams. So it just says that if x goes with output b to x prime and y goes with output c to y prime, then x O plus I, y can go with b plus c to x prime plus y prime. As a distributive law, it looks like this. So it's not too difficult to see how these two correspond. So here you can think of what you have on the left side is what you get from the coalgebra map. So these are elements of f of x, so to speak. Or it's a pair of elements from f of x. So for a slightly different example, you can consider this box plus, which is almost like the O plus, but here on the right-hand side you have no longer x prime, but just x. So I forgot to say, it's not difficult to see that the O plus is just element-wise addition of streams. But the box plus, it just adds the first element of the x stream to all the elements of the y stream. So as you can see, it's like the x doesn't move. You just leave the x in the state where it is. And this corresponds to what we call an abstract GSOS law. So these are the lambdas of the type where you have sigma distributing over the identity function times f, and it looks like this. So this allows you to use the x's that were on the left side also in your specification on the right side. Okay, so if we have an operation on streams, we can consider the Pointwise operation on stream functions, and it's just defined in the way you would expect. Now, if this operation sigma itself is causal in the k-area sense, which I think should be clear what that should mean, then also the pointwise extension will preserve causality. So if the input functions are causal, then the pointwise extension will also, the result of the pointwise extension will also be a causal function. So that means we can think of it as a map on the final Mealy coalgebra. So, so of course not all stream operations are causal. For instance, the tail operation is, well, clearly not causal, because you need to look one step ahead in order to produce the next element of the tail. But the O plus and the box plus operations are. So, yeah, the question we ask is, well, if the sigma comes from a distributive law, does the pointwise extension also come from a distributive law, and can be constructed from the law of sigma? So if we look at the examples we had before, for the O plus, well, you can think of, you have some operation on streams, and you think, well, if I just add input somehow to these rules, if you think, this says that the stream x can go with output b to x prime, and if you want to add input, you want to somehow say, what can x do on input a? Well, you say that if x on input a outputs b and moves to x prime, then you get kind of a naive approach to defining what the pointwise extension should be. And it turns out that this O plus, this works. So the O plus bar defined on the right is exactly the pointwise extension of the O plus to stream operations. But let's try to do the same with the box plus. Well, you get the rule on the right, but it turns out that this is not going to work. This does not work. Why does it not work? Well, if you just look at an example where input set is the same as the output set, and you consider what this box plus bar should do on the identity functions, well, then you see that if you follow the rule on the right, and you feed some alpha stream, A0, A1, etc. to it, well, then you get this sequence of transitions in the, well, in this kind of, in the Mealy machine defined on the right. And of course, this is not the pointwise extension of the box plus operation. So how can we fix this? Well, we need to, if you think about what happens, if you have some x on the right, so rather than x prime, you have just x here. When you feed some input, well, if you don't somehow register that in your rule, then yeah, something is going to go wrong. So what we do is we introduce another set of operators to the syntax, which are like buffer operators. So for each input element A, we have something called a buffer. So instead of x here, on the right we put a buffer x. And it turns out that it works. You can show that this indeed does define the pointwise extension of the box plus. But not only that, it works because of this general setup with lambda bialgebras, etc. It works for any GSOS defined operation and for any F, assuming you have final coordinates, of course. So there's a little detail, of course. First of all, for the streams and Mealy machine example, we know that the final coalgebra of the Mealy functor or the Mealy machines is, are causal stream functions, but for any F, it's not really clear why you would think of the F to the A behaviors as functions of this type. But it's not too difficult to see that you can associate elements of the final F to the A coalgebra with maps of this type by doing the following. So suppose you have a stream automaton S, and you have some F to the A coalgebra M. Then we can define an F-coalgebra simply by first we apply the coalgebra maps in each component. So here you unfold the stream automaton, you look at the successors, and here you unfold the M coalgebra, one step. Then you do some regrouping. And now you can see, well, now you can apply the natural transformation that just evaluates the function. So then you get a pair in y times f of x. Now you apply strength, and that gives you an F-coalgebra structure on y times x. So by finality, we get a map from this coalgebra into the final coalgebra. And if we in particular take the S and the M to be the final stream coalgebra and the final F to the A coalgebra, then we can really think of it as a map, as a way of associating functions from A omega to Z with behaviors from Z bar. So Z bar is the domain of the final F to the A coalgebra. And so yes, just to make a precise statement of what we mean by the pointwise extension, well, it means that if you have an operation, a sigma algebra, small sigma on Z, then the pointwise extension is the sigma bar which makes this diagram commute. Or it is a pointwise extension if this diagram commutes. So if you write this out in algebraic terms, it's of course just what you would say. So, well, the result is that for any simple SOS law, so where you just have sigma distributing over F, and you can do it for the free monad on the right also, you can extend this distributive law to one that defines the pointwise extension on the final F to the A coalgebra, and it's very simple intuitively. We've seen what you do. You just add input labels, so to speak, in the rule format. More precisely, you get the lambda bar simply by taking this composition with the co-strength. And for the GSOS laws, if the lambda defines some sigma algebra, small sigma, then we can extend it to lambda bar, which distributes the sigma bar, which is the syntax extended with the buffer operators, such that it defines a sigma bar algebra on the F to the A behaviors. And then we get the pointwise extension of sigma simply by composing with by injecting into the co-product, so sigma to sigma bar. And well, the intuition is again like what we saw in the example with the box class, namely that you add rules. So to get the lambda bar rules, you add rules for buffer operations, you add input labels to the lambda rules, and on the right hand side you replace every occurrence of x with this A for x. And I believe that was it. Thanks very much.
Thanks a lot. Questions?
Could I just ask about the scope of this work, in terms of how it's going? So there's a limitation to this if you want to do a whole class of basic SOS applications, as far as I can tell, in that if you take something like CCS, you have inputs and outputs, and inputs and outputs interact and so on. Whereas as far as I can pick up the bialgebra, it's only modelling situations where you're reading a stream of inputs and you're accumulating all the inputs and you're accumulating all the outputs and you're putting in the stream, so you can compose them in different ways, but they can't spontaneously and non-deterministically interact.
No.
So that isn't captured in this framework.
No. No.
And have you tried any extensions, any modifications which would maybe a further axiom or a further kind of property which you would add to the bialgebra to enable this property?
Well, first of all, of course, this whole setup it only deals with pointwise extensions, so yeah. Most of the well-known process algebra operations they are not pointwise extensions, right?
Yes, I'm just so, talking about specifically yes. This interaction, not the...
Yeah, exactly, so you mean communication
yes,
operations.
Specifically communication,
yeah.
Like simple communication.
Yeah. Well, certainly, I don't think that, that would not be an extension of our work, because it's just a completely different kind of interaction, right? Of course, in SOS, you can, well, let me see, CCS is where the action is the co-action.
Yes, yeah.
Yeah, I have to think. So, I have to say, SOS is not my own specialty. I think Kartik would be much better at answering this. But, there is certainly a lot of work done in dealing with various process algebras in terms of lambda bialgebra and, well, this category theoretical framework. I have to say, I'm not sure the CCS example has been properly dealt with. I know that synchronous communication can be... So
intuitively, like, what I'm looking for is something like a T-Hoff algebra or something like this, where you have an antipode as well in your bialgebra, so looking at generalizations in that direction, but perhaps you haven't No.
No, I haven't. I
Okay.
hear about
Well, thank you
this
very
whole
much.
flight was the first time I hear, so this is not something. But it could be interesting to. I mean, it would be interesting if there was some combination or some correspondence between the bioalgebras and F-algebras and these bioalgebras.
Okay, I think we should thank the speaker and move on.